Good morning. The following session, Writing Roads to How to Read a Math Book, will be presented by Mr. Tom Rosenwinkel, who is the sixth grade homeroom teacher and head of math at Memorial Lutheran School in Houston, Texas. He also teaches geometry, calculus, multivariable calculus, and linear algebra in the upper school. Please welcome Mr. Rosenwinkel.
Thank you. The quadrivium is a united whole, just as is the trivium, and all of the liberal arts actually. A united whole that frees our human minds to learn, that is, to receive or increase in knowledge from outside ourselves, from other instructors and authors, and ultimately from the special revelation of Holy Scripture that is already ours. So I left off last year with this Nicomachus reference to Plato's 13th book of laws. So probably not directly Plato, actually. In his Introduction to Arithmetic, Book 1, every diagram, system of numbers, every scheme of harmony, and every law of the movement of the stars ought to appear as one to him who studies rightly. Even if we wish to establish mastery prerequisites to direct the order of studying the four arts of the quadrivium, as Nicomachus himself does, ending with astronomy, though Plato had harmony at the end of that list. We should share the end goal with Nicomachus to study all four of these arts. They do make us most ready to study philosophy by giving us multiple perspectives from which we can see a united or pure truth with increasing clarity. Each quadrivial art can play a part in finding and sharing the truth of a mathematical matter. The best scholars can find more than one of these perspectives and evaluate which would be best to share. Nicomachus writes in Introduction to Arithmetic, Book 2, Chapter 24, in paragraph 3, the geometric proportion has a peculiar property shared by none of the rest, that the differences of the terms are in the same ratio to each other as the terms to those adjacent to them, the greater to the less, and vice versa. Still, another property is that the greater terms have, as a difference with respect to the lesser terms themselves. And similarly, difference differs from difference by the smaller difference itself if the terms are set forth in the double ratio. In the triple ratio, both terms and differences will have as a difference twice the next smaller, and in the quadruple ratio, thrice, in the quintuple, 4 times, and so on. Now, I know you don't read this for amusement, or even for practicality. Unless you are a very weird person, you probably don't read it at all. But you came to this presentation to learn about reading a math book, and this is one of the most profound paragraphs ever written in a math book. So in our first 15 minutes, I'm going to present to you a close reading. I'm not going to teach you the math, but show you some of the power that a close reading in math can unlock. Now, with 11th graders at our school, I can present this 20 minutes at a time and return as needed according to attention and focus. For the sake of our time today, I will present the entire thing in 15 minutes and ask that you please ask for details at a later time. But after this close reading, I will talk about how to read a math book and show examples at increasingly lower grade levels of math. So first, you need to know that what Nicomachus calls a proportion, we call today a sequence. So his geometric proportion is what we call a geometric sequence. And he gives us 4 examples and invites us to think inductively with him to see this peculiar property shared by no other type of sequence. So here is a double ratio. As we call it a sequence, we can see that each number is double the number that precedes it. The differences with each greater term with respect to the lesser are in fact the original sequence itself. 2 minus 1 is 2, 4 minus 2 is 2, 8 minus 4 is 4, 16 minus 8 is 8, in that arrangement there. So here also is a second difference, and notice that if the difference was the original sequence itself, indeed subsequent differences will also be the original sequence itself. So this is the first of these two sentences. It's only a two-sentence paragraph, but of Nicomachus. We're not supposed to do that in 6th grade. It's apparent when we see that the ratio continued in these differences is indeed that double ratio in the last slide, exactly the original sequence itself. The double ratio is a 100% growth rate. These different sequences are 100% the original sequence. So here's the triple ratio, which is a 200% growth rate, and its difference. And notice the ratio between each term of the sequence is triple, and this is true for the different sequences as well. And that is Nicomachus's first sentence. Reading from left to right, we could say times 3 is between each number. So notice next that each difference is twice the previous sequence, and that's Nicomachus's second sentence, that 1 times 2 is 2, 3 times 2 is 6, 9 times 2 is 18, all down there, and that makes the second difference quadruple the original because it's times 2 times 2, and it would continue in that pattern. That's the second sentence that Nicomachus is giving us. It's because each difference is the 200% growth rate of the previous term, building the triple ratio. So here's the quadruple and quintuple sequences and their first and second differences. Notice that each sequence continues the same ratio, but that each difference of the quadruple sequence, which is a 300% growth rate, is triple the sequence above it, and each difference of the quintuple, which is a 400% growth rate, is quadruple the sequence above it. We can put symbols around this to capture the generality and universal nature of this numerical property. So what is common today is to call a sequence with a letter A and use a subscript to indicate the location of a number within the sequence. It is common to call the growth rate R, and then each term in the sequence can be calculated by starting with the initial value denoted A sub 0 and multiplying by 1 plus R every time. The previous term, each term is the previous term with its growth compounded for each step in time. Because each number in the sequence is the one before it and the growth of it, which is this denoted as 1 and the growth, the 1 plus R. And with these symbols, we can express this property in terms familiar to us as distributive properties. It is interesting that this argument applies not only for multiples of 100% growth, but any factor of growth, fractional or not, and even negative growth, also known as decay. Now, as a close reading, we can continue the same argument with subdividing each step in time and compounding by some frequency that we commonly call m. The difference will have m of the growth subdivided by m, so that it is the same growth proportion that is maintained term to term. Now, as a close reading, I understand that the symbols are way beyond the way Nicomachus wrote, but where they're a common way we would write it today. And as a close reading, we'd also recognize today that increasingly compounded subdivided growth finds Euler's exponential function as its limit. Now, if you're not familiar with the symbolic description of exponential growth or the calculus notation I'm about to use to describe it, I just want you to see that this very property we are reading from Nicomachus in AD 100 grounds Euler's 1748 insights into trigonometry 3/4 of a millennium later, and which are still unmatched today. And in particular, though Euler derived his series representations for trigonometric functions using trigonometry, he was also a master of integration by parts. So I want to show the patterns and structures that emerge from integration by parts without appealing to trigonometry. And it's worth a few days in 11th grade to teach integration by parts, but I understand that not everyone here will understand the details of the next 2 slides until taking additional time after this presentation. You can hold your laughter to the end to make sure I get through it in the 15 minutes that I promised. Because here is the fundamental theorem of calculus For Euler's exponential function, it is a way of expressing the value of this function, beginning with its initial value, which is 1, and accumulating the derivative or the growth rate up to that time t. Integration by parts allows us to calculate more of these terms that involve only the initial values of the additional derivatives, which are increasing powers of r according to Nicomachus's property, and the final values of the antiderivatives, which are powers of t. And this is for the sake of reference, for the thick calculus. It's a convolutional form from the fundamental theorem of calculus, and this is what ensures that as we are generating these terms, which are the Taylor series expansion of the exponential function from its initial value, that the final value of the exponential function is never needed because the final value of that power base is 0. So the initial values of the exponential derivatives are the coefficients of the increasing powers of t, and they have the increasing powers of r from that property from Nicomachus. And here are the first 9 of those terms. And our property of increasing powers of r applies as well when the growth rate is imaginary. Pastor Kane just reminded me that that's his favorite number, the square root of -1. That is also the solutions to simple harmonic motion. And because the powers of I are cyclical, we can collect real and then imaginary terms, and note that all the real terms are even and all the imaginary terms are odd. Note that we'll want to note a lot of other things. If we calculate the size or absolute value of the complex values of this exponential function, it's those even and odd properties and exponential properties that show that the size will always be no more or less than 1. All values of this function lie on the unit circle of the complex plane. To emphasize, the size of the value of a complex exponential is exactly 1, regardless of the value of t. All the values of this, in fact, we can see that the initial value for t equals 0, that would be 1 in the real part and 0 in the imaginary part. Now, following a clever path of analysis from Walter Rudin, we can note that by the time t equals 2, the real part is negative. In fact, it's less than -1/3, because we can calculate that. And because these are polynomials, which are continuous, we know that there has to be some number for t exactly for which that real part is 0, decreasing from positive to negative. We call that special time number rho. And then as a special number, I should note that it's not necessarily a rational number. And in fact, it is an irrational number. It's a little more than 4/7 of the way between 1 and 2. So at t equals rho, the real part of the complex exponential is 0, so the imaginary part is 1. Because the square of the imaginary number is -1 from Pastor Kane, we can write with Euler that e to the I rho squared is -1. And in fact, then every 4 rho, these components of the complex exponential values will repeat, going around that circle. From multiplying 2 complex exponentials and checking the results of multiplying 2 complex numbers together, we see that we have the same forms as the trigonometric sum identities. So now we have shown enough to call the real part cosine and the imaginary part sine, and without drawing a right triangle. We've shown that algebraic properties of complex numbers are enough to completely define the trigonometric functions with no geometric prerequisite, only Nicomachus's property of geometric sequences extended to continuous growth with pure imaginary harmonic growth rate. So trigonometry belongs to harmony as much as it belongs to geometry. We did not even define the number pi, but we see that it is twice that special time number rho that we found to establish the frequency of the motion. So the way our 10th graders prove the angle sum identity is through Ptolemy's theorem and Almagest. The red triangle is similar to the blue triangle of 1, 2, 3 correspond with 1, 2, 3. And the 3 triangle is similar to this 1 triangle of red, yellow, blue, red, yellow, blue. And that provides that same proof of the trigonometric identity from Ptolemy. And so this is an example of finding a same one thing, trigonometric functions, whether we look from arithmetic and harmony or from geometry and astronomy. Most deep studies in mathematics are interdisciplinary in nature. Polynomials, matrix algebra, advanced integration techniques, just to name a few other examples. Insights from all 4 quadrivial arts are often necessary or at least advantageous for discovery and instruction in these mathematical studies. The greatest and most beautiful math books will leverage multiple quadrivial arts to convey profound truths. So now this presentation will be on how to read a math book. Whether or not we wish to shape our working math curriculum around the great books from across the centuries, we should expect that adults can read them. If adults cannot read them, how will they be passed to the next generation? While it is an open question whether all 4 arts of the quadrivium belong to a U.S. high school education, I say today that we best serve our future adults by equipping them to read a math book, by developing skills in all 4 arts of the quadrivium founded on the 3 arts of the trivium. So in fact, just as reading from multiple sources and composing a research paper prepares one to discern and read greater source texts, learning all 4 arts of the quadrivium equips one to discern and read greater math books. I will not single-handedly answer the question how to read a math book just today, but if you can remain through this whole presentation, I hope you will find some helpful instruction on how to read a math book to children. There can be some problems if we don't know how to do it right. I'll give some practical writing examples that I've found useful. So in 1940, Mortimer Adler wrote a book called How to Read a Book, and it became a bestseller. He rewrote this book in a new edition in 1972. Now, Adler is not as near and dear, maybe not as insightful, and certainly not as theological as Melanchthon has been in our other presentations this week. But finding something refreshing from the 20th century is fun. So most of what I'm about to say about how to read a math book is not my own, but the best I've taken from his books as well as a few other places and applied to my own attempts to go back and read and teach math books. So the way to really begin thinking about it is to ask, and you can raise your hand for this, how many here have read a math book before? Okay. Somewhat confident. Americans are very confident in math. Now, most Americans, I can also say, probably just don't know how to read a math book. And that is not actually a rude thing to say, just when Adler said it about Americans not being able to read a book. But it's because we have to look at what we mean by reading in our question. So the better question, the more honest question for us here is, how many of you have ever missed anything from a math book? Actually, more people than raise their hands who have read a math book. I was not expecting that. Okay. So our first order of business is to be sure that we are not here to read math books simply by reviewing or skimming the surface of the facts from these books, as if a great math book will teach us this is a number, paint it this color, or how to do such and such, or as we're trying to read this is a VCR and this is how to set the timer. We will find that the best math books have something to teach us which requires more than elementary reading for facts or contents. So reading is learning. Learning means that we know, understand, or comprehend something that we did not previously know, understand, or comprehend, something new and something that the author has and wishes for us to have as well. Especially in math, this only happens by reasoning through it ourselves, finding enlightenment together with the author. We do not read math books or learn in math class by outsourcing the thinking to the author or teacher. So just as Adler wrote about, we should not read great texts the way we read magazines and newspapers, where some author has done the investigative and critical work for us. We should not read math books the way we read instruction manuals and cookbooks. And in fact, such reading may actually be counterproductive to our learning, and I won't go so far as to call it anti-reading, but there is a real danger that when we read something great as if it were technical instructions, we train ourselves to overlook the good and beautiful and miss the truth we would demand and should demand from a real math book. There's a place for procedure and production in a math book. That is also why we must reserve a place for true learning, understanding number, distance, time, or spatial representation in a different way, or at a higher level of abstraction or meaning than we did when we first began to read. So what is meant by reading math? And it is not the same as what you probably mean when you say doing math, and it's not even the same as when you say growing our math ability. So I want to talk about that a little bit. We don't have the same ability concept in a lot of other subject areas. What is our history ability, or our literature ability, or theological ability? We do have expectations on what to read or learn from history books. We expect first to better understand the facts of a historical matter, but further, we wish to learn about ourselves through the wisdom and folly of those who came before us, and we wish to learn the same about ourselves from the greatest works of imaginative fiction and literature. There are techniques for reading history books, literature books, geography books, and science books, and as much as we appreciate mathematics as a distinct study, we must understand that there will be some distinct techniques for reading math books. We will have a certain level of reading ability to learn and read a math book, and so we should ask, what is the truth we learn from a math book? The truth of a math book is eternal and universal, differently than what we find in other books. In the humane letters, we appeal to authoritative texts to establish the truth we can find in a matter. In medical and other sciences, we trust in professionals and long-standing conventions and keeping those subject to progressive observation to show us the truth of a matter. In law and politics, truth is established through institution and persuasion. In math, truth is established logically through proof. And it's important to understand how strong this word proof is for a mathematician. Proof is the last thing you want to find when reading an instruction manual or a cookbook. It is an absolute confirmation that truth has been found in a mathematical work. Most math books for schools today, what we call the textbooks for children, do not value proof for developing the reading and writing abilities to express proof the same way as computation and routine and instructions. Even if there are the best mathematicians of history are the most able in the skill and art of proof, even if there are proof mistakes in their own great works, not different in nature to Nicomachus referring to Plato's 13th book of laws. Now, here is the first most common challenge to reading a math book. Have you ever felt like the only way to get through a piece of math book is to already know, understand, or comprehend the book or what the book is supposed to be teaching? Now, it would need to come from someplace extrinsic, not intrinsically accessible from the very book you are attempting. In case you need a reminder, you probably felt like that about 15 minutes ago, and I told you that you would need to come back later for those details, lots of details. Readers of math books must be diligent and patient, because proof is very precise, and it's technical, and it's a complex communication. And a great author will enflesh it in perspective that will make it then clear. When a mathematician writes, elegance is to say as much as possible universally and timelessly in as little as possible. A uniting principle of the quadrivium is abstraction. Abstraction, especially in symbolic terms found in abstract algebra and the thick notation of calculus, may be difficult for the ages of children we are teaching, which is exactly why children need teachers familiar with their age and development to spend time and effort with them, providing them the same advantages as reading aloud to children before they know how to read. Children understand and appreciate mathematical truth long before they can express it abstractly, symbolically. Adler connects reading books with listening to teachers. In both reading a book on any subject and listening to a lecture on any subject, we need to submit ourselves to the speech and teachings of another to share the enlightenment, which may or may not work at first or ever. With a book, there is more opportunity to skip backwards and forwards, which gives the reader some advantage. But with the teacher, there is more opportunity to pause entirely to interact, which is a great advantage. Children need to be trained on both how to read well and how to listen well. This will be more important for math than other subjects because of the patience and diligence required. My oldest daughter, when I found her adding instead of subtracting her 4-digit numbers in her workbook, would smile at me and erase, and she'd say, "Oh, sorry, I forgot to listen. I did plus when it said to do minus." And of course, by listening, she meant reading the symbol from the workbook. Same if she accidentally wrote her answer to 3 plus 5 when the problem asked her to write the result of 8 plus 5, she would just say she needed to listen, which really meant pay attention. So it is reading, listening, writing, and teaching math that requires skills and abilities. I will suggest that the skills and abilities people usually describe as math skills are really the skills that prepare the mind for reading a math book or listening to a math teacher. Keenness of observation, readily available memory, range of imagination, and of course, a reason trained in analysis and reflection. So reading, listening, and teaching math are arts, just like the technical arts, fine arts, and most proximally the language arts. Diligent practice develops talent. From antiquity, the mathematical arts of the quadrivium have followed the language arts of the trivium, not because they are separate from the language arts, but dependent. And I'll read these same skills, usually considered for math readiness, again, but provide the full quote from Mortimer Adler as he relates reading with listening and learning. The art of reading, in short, includes all the same skills that are involved in the art of discovery. The keenness of observation, readily available memory, range of imagination, and of course, a reason trained in analysis and reflection. These skills are maybe even more important for reading a math book than they are for reading a book in general, or for discovery in general. Just a quick surface level etymology search would tell us that mathema is that which is learned, or the object of study. So we have reading is learning, and math is what we are discovering when we learn. Classical schools are known for producing students who read whole books. And the more we unite every liberal art, not only the trivium, we will be just as well known for producing students who can read math books and learning from math teachers. And certainly keenness of observation and readily available memory are necessary for the technical precision and stark rigidness of mathematical language, but range of imagination and reason trained in analysis and reflection are most necessary for the abstract nature and beautiful elegance of the best math books. And they develop another taste that classical schools are known for cultivating like nowhere else: taste for dead things. Adler tells us that reading great books is to learn from dead teachers, not only listening to living ones. But today I have a different dead thing for comparison with math. Because Latin is a rather dead language, it's a great vehicle into ancient thought. Because we haven't corrupted it too much over so many centuries, proven mathematical statements are corruption-proof. Once Nicomachus proved his proportional growth property for geometric sequences, Euler could expand on it, but not displace it, like a better germ theory or gravitational model. Proven mathematical statements are eternally dead, and the mathematician's name is known as the most immortal among our fallen authors. Parenthetically, if we forget those mathematical truths, we need to kill them again. It's like a bad zombie movie. But there is another freedom found once a taste for dead Latin is developed. That is a freedom to think and work within the arts of language that is uninhibited by the abuses of a living language. Latin and the other dead languages form a playground for learning the language arts, which we cannot recreate with our own language, any currently spoken second language, or even a widely spoken second language. To enter this kind of playground, one needs to learn a dead language. The playground of the quadrivium will be even more dead, the language of number sets and their relations. These number sets and their relations are our best expressions today for the central unifying systems, diagrams, schemes, and laws that Epinomius wrote in the quote from Nicomachus on the first slide. These are the dry, dead characters whose traits are immutable, stated and proven eternally, whose expressions are found wondrous and beautiful once their abstract and symbolic nature is learned. So our schools are known for students who translate Julius Caesar from Latin by their senior year. It's because that is the best way to learn about his history, the most careful study of a primary text. However, we do not wait until the senior year to introduce them to Julius Caesar or how he changed the world. We should not wait until their junior or senior years to introduce them to the full range of number sets and their relations in space and time, understanding that they won't be doing the highly symbolic translation work for many years. There's a lot we should do to focus on writing and therefore reading and learning math at an age-appropriate level, introducing advanced concepts earlier before the symbolic maturity is there. And as those of you who teach reading know, there are various levels of reading. Now, in his 1940 edition, Mortimer Adler advises passing through a book 3 times and learning how to read a book. So though the first 2 can be done simultaneously once a certain level of advanced skill has been developed, similar to how a musician can focus on pitch and rhythm simultaneously at some point while learning for mastery, or a driver can watch traffic simultaneously with driving, but not at first. So this diagram puts these various sub-processes together into a single infographic on his advice on how to read a book. The first pass begins at the top and enters the book, which is the disc toward the bottom. The second pass comes up out of the disc, goes back to the top. So it is a process of understanding what the book says, first from its title, contents, outline, but down to its words, coming to terms with the author, meeting with the mind of the author to learn the new knowledge conveyed from the author to the reader. Now, in a third pass or final pass, separately from up above, Adler teaches how to read critically. That's the very bottom underneath the disc. So all along, this is an interactive process, how to read a book. The best way to form it into habit is to train the mind through writing exercises, annotation, note-taking, outlining, and composing a critical response. Adler describes writing and reading are reciprocal as are teaching and being taught. The reader tries to uncover the skeleton that the book conceals. The author starts with the skeleton and tries to cover it up artistically. And it's this artistic practice in the trivium that frees the mind to read and learn, write, and teach. Adler explains how great book authors enflesh the skeletons of their narratives, arguments, histories, etc., with figures of speech, syllogisms, rhetorical devices. So we should practice the trivial arts to become better readers of books. Great math book authors will enflesh the dead number sets and their relations with numbers, magnitudes, dynamics, and contours. So all 4 quadrivial arts are helpful to become better readers of math books. All 7 liberal arts will help us meet the mind of the mathematician and comprehend the abstractness of a math book. Together, they help us understand the unified picture. So when reading about trigonometry, a harmonic perspective is highly advantageous, just as is a geometric perspective. Even if either perspective alone is mathematically or logically sufficient, our human minds are enhanced by both. When reading about algebra, a geometric perspective is highly advantageous, just as is an arithmetic perspective. And when reading about matrices, any of the 4 quadrivial arts may be the most advantageous perspectives in various circumstances. If our mind remains unshaped by only one art of the quadrivium, we would have a more difficult time reading a math book. Last year, I read with the rest of our teachers a book called The Writing Revolution 2.0 by Hockman and Wexler. And these authors give practical examples of writing exercises for all subjects and grades and show how the writing exercises advance thinking in these subjects at various grade levels. Among many benefits to a writing-oriented approach to learning, the authors report studies have found that when students at any grade level write about texts they have read and content they have been taught, Not just in English, but also in social studies, science, and math, their reading comprehension and learning is enhanced. Writing across disciplines can improve reading comprehension, critical thinking, and disciplinary content knowledge, according to a panel of experts convened by the U.S. Department of Education. Adler's 1972 edition of How to Read a Book expanded his 3 passes, which is the diagram on the left. He expanded it to 4 different levels of reading. So these expansions are helpful for teaching us how to read math books with children. So what I've shown in those 3 passes, and really only talked about the first 2, that's what Adler calls the 3rd level of reading in 1972, analytical reading. The 2nd level is like an introduction to the first pass within that 3rd level, at a time when speed reading was becoming popular within American reading culture. Adler advises how to quickly pick up the contents of a book, which is a higher level skill than elementary reading, but a lower level than critical or analytical reading. So I'd like to talk more here about Adler's 1st level of reading, which he calls elementary reading. He describes the process of learning elementary reading in 4 stages. Reading readiness, resulting in an alphabetical literacy, which happens in early years. Word mastery, resulting in simple literacy in the 1st grade. Vocabulary growth and contextual understanding, resulting in functional literacy by 4th grade. And mature reading, resulting in mastery of reading at this elementary level. These are foundational in the Writing Road to Reading curriculum, which I've not used myself, but seen in several classical homeschools and schools. So the reading teachers here probably know this, and the math teachers may or may not. I hope it's helpful to see it all in one place. If we take what many of us call the march to calculus and call it a progression of learning to read mathematics, it makes sense to see a development from reading digits to reading algebraic expressions to reading symbolic calculus and analysis. Just as stages of reading need to be filled with great content from all subjects, the stages of reading math must be filled with the great content from all the objects of study in the quadrivium, the numbers, magnitudes, dynamics, and contours. Practicing writing expressions and diagrams with these will prepare for the alphabetical, simple, and functional symbolic literacies that children will not actually develop until later. Technical mathematical statements are more precise than any language naturally expresses. So while words are pliable and hence require analytical reading skills to translate from words to terms, sentences to propositions, and paragraphs to arguments, a closed, fully quantified, symbolic, mathematical definition, postulate, proposition, theorem, lemma, or corollary says exactly what has been written, no more and no less. This is true not only for expressing statements, but for expressing proofs. If one line or part is missing, incorrect, or unclear, the whole proof fails. It's also like encoded software. If one line or part is missing, incorrect, or unclear, the whole fails. Patience and diligence are worthwhile once one can actually, fully, completely read a math problem. It can be solved almost instantly, the only impediment being the speed at which the solution can be calculated and written back to the teacher or author. If you happened to understand the symbolic formulas in that close reading, only because I showed them first with digits, and then also only because Nicomachus gave just enough example sequences, then you experienced that mysterious jump from the alien abstract sentences Nicomachus wrote to understanding at least the ratios. This is just like a first grader reading a word after forming just enough of the sounds to recognize it. And this jump from alien symbols to learning and understanding is a quite mysterious transformation. Adler describes that it happens twice for language, once in the first years of life from sounds to words with meaning, and again around first grade from symbols to words with meaning. Since math is a written language, Adler says it happens only one time. I'd like to go further and suggest some stages of math reading that jump from simple to functional and from functional to mature symbolic literacy. And those are the jumps between stages of comprehending and expressing abstract mathematical truths, number sets, and their relations that are age appropriate. So like reading language, these various jumps will happen earlier and more solidly when we teach by reading aloud and assign active writing exercises in readiness in these preceding years. When learning to read, children hear first their parents' voice and teacher's voice before they hear their own voice, even when they are learning and practicing reading aloud. So the strongest foundation for calculus will be strong writing skills, building the notation early but gradually, some examples of which I presented with the entire presentation last year. And also for calculus, there should be a strong foundation in writing algebraic and trigonometric expressions. Strong writing skills with digits and place value provide a solid foundation for algebra. In the close reading I presented from Nicomachus, it was helpful to write the numerical sequences and then write them more generally in the algebraic symbols and then state the property abstractly. And then I did add some calculus notation. But to help an algebra student learn to express and write algebraic expressions, it can be helpful to write an additional version of these sequences, powers of the base number. Here are the double ratio differences, and the differences are the sequences themselves, and they're shifted so that the same sequences can be seen vertically as well as horizontally. The triple ratio shows the interesting property that the powers of 3 increment horizontally, but because the differences are shifted, these powers of 3 decrement vertically, while the powers of 2 increment with each difference. Here is a symbolic expression to capture this property. It holds also for the quadruple. You see the powers of 4 increasing left to right and decreasing up to down, while the powers of 3 are accumulating or incrementing. And same with the quintuple. Also, you might notice that these are the super particular ratios Nicomachus described in his earlier book, the sesquialter, sesquitertian, sesquiquartan, and so forth. Now, writing it in this form, we see the pattern more clearly and find that we value less the digits in base 10, and we value more these powers, the power formulas, which is precisely our motivation for characterizing them with symbolic algebra. We should remember that digits in a place value system are abstract symbols, just like calculus and algebraic expressions, expressing numbers in various base systems, especially 2, 3, 4, 8, 16, and 60. They're also expressing numbers as unique products of prime factors. Those are all essential writing exercises. But with my remaining time, I'd like to focus now down to 6th grade. It's important when in 6th grade that they start thinking about more than one number at a time, understanding their relationships and moving toward reading and writing compound algebraic expressions. Similarly, in 6th grade, we start reading about more than one source at a time about a historical topic or narrative, ultimately moving toward writing a research paper. So this requires more reading, deeper reading, and slower reading as they are achieving or continuing to benefit and improve on their mastery of math facts. At the very time, they're needing to connect with a reader in their writing composition class, which requires feedback. They need to learn to develop independence in their math reading, which requires them to check their work for their own feedback. The process of reading and comprehending a math problem becomes instantaneous with its solution when it's done well. It's when they cannot read the problem. That's when they seek dependency on friends, teachers, calculators, and those machines do not read, or anything within reach. So I start by asking them to write the problem either in their own words or their own symbols, but for 2-step problems, which often require a great leap in reading ability, I help them read the first part and I help them read the first part of the problem, but ask them to ask themselves, what is the question that is begged? By actively reading and answering that question, sometimes the rest of the question can be read more clearly and answered instantly. So if I give them just this much, they don't like not knowing what's the question. So I have to ask them, what is the question that is begged? And they might come up with a few different questions that are begged, but as they think about just what is the question that is begged, they might start to write some nice things. Like they can write 100% of the price was $11.20. And from there, they can write 10% of the price is $1.12. And sometimes they don't write the phrase of the price, even though it belongs there. But they're thinking through and they're reading the problem closely. Because then they can write some more things from there. They can write 5% is 56 cents, 20% is $2.24, 15% is $1.68. And the competitive ones will write 120% is then $13.44. And sometimes they stack and work their processes, and sometimes they do it mentally. It's the reading that is so great. And so they do all of this without being distracted by the actual question, but by the time they see the actual question, they're fine. And it's wonderful. In sixth grade literature, when Rosemary Sutcliffe's Judish barbarian, Old Bruni, sees Aquila reading Homer's words from old symbols, as he learned in his youth from Roman Britain, he thinks it's magic at first. When sixth graders read multi-step problems so well that they complete them mentally, it's because they are thinking through their reading and writing of math. The technology indeed slows them down, which sometimes they need and sometimes they do not need. When they compete, solving multivariable algebra problems mentally through careful reading, it looks like magic to us. So the difference between absolute change and relative change is also an important jump in reading readiness for understanding the art of number in time. Here's another problem that is understood easily once it is read well, but it seems very inaccessible until the instant it is learned. So there are twice as many carnations as roses in a flower shop, and after selling 50 carnations and 10 roses, there were 3 times as many roses as carnations left in the shop. Most people who have been through an algebra class, and that's going to be then most of the tutors that families might hire for their sixth graders, or teachers. They want to write algebraic equations and solve for multiple variables for this problem, but that's not accessible and does not need to be accessible to sixth graders. However, some sixth graders are motivated to learn some algebra when they read through and think through problems like this. But as a writing exercise, advanced reading skills, practicing the art of proportion and number in time, the absolute and relative change. Sixth graders will solve this problem with mental math, and the writing exercise here is actually a visualization of bar graphs. The sixth graders wrote, we beg the question, we beg to express the most elementary number first. That is key for this one. The most elementary number would be that since the number of roses at the end was 3 times the number of carnations, we use that number of carnations as a most elementary number. So begging to express that, we just work our way to expressing through these various pieces, 3 times as many roses at the end, 3 times as many carnations at the end. That's the number of roses at the end, but the number of roses before was that and the 10, and they don't like at first, not knowing relatively how much is 10 compared to those other ones. We don't know, and they have to design first because we're reading first before we actually draw the perfect bars. It's drafting like their maps and like their essays, drafting and designing. But reading, we can continue reading because we know there were twice as many carnations before, and the last step then is that last difference of 50. So when we've read the problem entirely, then we can write that 50 is 5 times the elementary number that we're begging, 5 of those and 2 tens. And then they say, well, that means that 30 is 5 of those. And then that means that elementary number is 6. Once they know that is 6, then they can write the perfect bar graph, which they like to then go and do. And they can answer any question about this situation. So recitation content and practice is also critical for learning to read math, but I'll need to talk about that another time. When I was writing this presentation, my 7-year-old forgot her long division. She does not like when that happens. She requires attention to soothe. She wanted to know 786 divided by 6, and so she should start with the hundreds. She should rewrite the number as 600 and 186, but further, she could see 600s and 630s and 6. So 1/6 of 786 is 130 and 1. So rewriting a number this way, the art of arithmetic, she could also divide by 3 the same way. She would rewrite 786, and so she would find dividing by 3 would be 200s and 60 and 2. She could rewrite the number if she had a different question about this number. If she was to subtract 97, she'd want to rewrite it as 789 and removing the 3, because then further removing the 97, she would see that she would get 689. And then dividing by 12, she could look for a multiple of 12. 786 is 720 and 60 and 6. So dividing by 12, she would see 60 and 5 and 1/2. This rewriting is just like what my 17-year-old will do next year when he rewrites an integral that he does not know how to do as another integral, which at least he would know how to do because they would recognize through rewriting their trig functions like they practiced last year in geometry that it's a very special number, pi. I need to end, so I'm going to go back to our youngest math learners. We do not need to wait until children can read in order to read math with them, just like we don't wait until they learn how to read before we read books with them. The playground of the quadrivium gives us more than enough ways to read through a small number of profound mathematical truths, even with our earliest learners. When they arrange blocks in a 2x5 array, and then they count the same 10 as when those blocks were arranged as 5x2, they are practicing astronomy to understand a deep one truth, eternal truth, that we call the commutative property of multiplication. When they find patterns and sequences so they can know which flashcard they will see next, or what tone they will hear next in singing. They are practicing music, and really they are understanding abstract cyclical group properties and ordered proportions. As much as they can listen to their teacher and ask questions, they know the answers because the abstract truths are eternal. So the first activity I do with my children is counting, with the two of us just alternating between odds and evens. It's a lot like reading a book. In fact, it's developing reading readiness. It is the abstract, eternal truths of mathematics that they can find accessible at their age, just as it is important to teach the specially revealed truth that already belongs to them, also accessible to them at their age. Thank you for everything that all of you do for classical Lutheran education. And we have time for questions. Yes?
You do classical conversations. Are you familiar with the math map that they just sent?
I saw presentations of the math map before it was released. I have not used it myself, but I've seen it. I've known people who have used it.
Okay. This will be the second year that.
Right. It is still very new. It introduces notation very early. And by practicing with that notation, the idea is that they become comfortable with the notation. What would be important is also to be sure that they are using the notation not as drilling and just rote practice, even with stranger symbols, but that there is some content behind it. That, I think, would be the challenge with the math map. And I say think it would be, as in I have not used it. I've gotten mixed reviews that we can talk about maybe afterwards. But I hope that's helpful about the math map. It is a classical math curriculum developed by engineers, which we need. Math curriculum that prepares future engineers so that they are doing the same things as their college roommates. Maybe they should be better readers than their college roommates. Jack.
Thank you. You talked about the dead language, so like with dead languages and teaching more ancient truths, and then you made that comparison to like the number sets and relations, the number sets and the relations. And the thing that I thought was curious about that is there not a sense in which like it's like we're surrounded by English, right? And then that's the advantage of Latin is we're not surrounded by Latin. One of the advantages of Latin is we're not surrounded by Latin, and so then that's what allows us to learn the grammar. But I wonder if just in general for mathematical content, like we're not in the same way surrounded by, like we're not by osmosis taking in like algebra.
Right, we don't learn to speak math the way we learn to speak English. And so we don't learn to speak in Latin. Like when we introduced Latin into our home, and my 7-year-old, who's now much older, but was just in tears over it. I just had to say, it's not your baby language, because when you learn your baby language, you are making baby mistakes. But we don't actually have those baby mistakes with math the same way. Now, the thing is, it's because we never learned to speak it in the first place. We just learned to write it and to read it written, and it is so symbolic that it actually just happens so much later. It's more like it doesn't happen, so we don't have the same baggage as with language. And in one of my conversations last night, I didn't call Latin an absolutely dead language. So I don't think we have a fully dead language, but I mean, it's just more dead than any of our current languages. Yeah. All right. Up here first and then back there.
I just wanted to express my appreciation for this definition of math being a dead language because of the world in which we live relative to English and a living language. Like we all know that when we say something's cool, we know we're not actually talking about the temperature of that thing. It's part of our cultural changes to language. Whereas with the symbols in math, there are not cultural changes to those symbols.
Yes. Nicomachus and Euler can have a conversation. Kind of has to go only one way because one came before the other, but they can talk about the same exact thing, and it is a unifying subject in that way. When people say math is a universal language, I think that's also just because it's not tied down to any one time or place. Yes, there's another one back there.
With the Nicomachus text at the beginning, you took a moment to say, okay, this word proportion that actually means sequence.
Yes.
To what extent should we be kind of doing the same with our students? How much is too much when it comes to making those texts more accessible?
Yes. Important for first the teacher to read the text, because I didn't say, to be very precise, I did not say that what Nicomachus calls a proportion is a sequence. It's just what we call today a sequence. And that same art of expression or enfleshing the dead math, we can do for our students through our vocabulary and our notation. And so just like they're learning vocabulary in younger grades and other subjects, in the high school, I try to be very consistent with my notation so that in the 11th grade calculus, I just use t as the independent variable. And if I'm using problems from another textbook, I retype them. Takes a little bit of time. It's just a retype, but it's worthwhile because that way they're not as focused on the letter itself, and they can just get used to a letter, but then they're focused more on the concept of the calculus. And so if we're reading Nicomachus with high schoolers, we just have to teach the vocabulary. And that's why I said that at first, actually, also, is because if we're going to read Nicomachus even here, we won't get very far at all if we don't know what he means by the word proportion, because he's talking about proportions. And we just mostly happen to know those called sequences, just in our books today. I hope that is good. Okay.
Going back to the question about Latin and experience for the student be working with base 10, which they're natively familiar with counting, versus learning another base, like base 2 or base 60? Could you talk about like what's the experience for the students? Do they think differently
Yes.
working with a different base in a similar way to they can think differently about language when they're dealing with flat 10?
That is one of those jumps. So when I first introduced some things like different bases to sixth graders, and they don't have the same earlier background, and I didn't introduce it to them with them until the end of the year, so I didn't give them that background myself. And fifth graders also, I went into the fifth grade and with our own children, but that there is first always a desire to express a number in base 10, and it is because they are familiar with base 10. So it was the ones that I introduced with those children most recently were counting permutations. And I did not use the word permutations with them. I just counted arrangements. We called it spelling, like how many ways to arrange letters. And I didn't even use the word factorial. I just said bang for an exclamation point, because that's a nice way and a fun way to just represent counting and the art, get that art of counting down. And as much as they loved the bang and different bangs in the denominator to account for indistinguishable objects, which is quite advanced for those ages, they still always wanted to know what was the number in base 10. And so they would use a calculator and they'd find a really big number. But the more they do it, the more they also find it's pretty worthless, all those digits. And then it's helpful to understand that sense of number for itself. And so that is all pre-exercise toward a jump from base 10 to other bases. And then that jump to other bases helps to motivate the algebraic or symbolic expressions. There might have been a few others. So, Nathaniel.
This was fantastic. Thank you so much. I just wanted to thank you especially for what you said about word problems. I don't know about everybody else, but I've always said, like, look for the question first. And that's like dumping information on somebody and then being like, so what do you think about that? Like, no time to process. That's such a good idea to force the kids to understand the situation, and then we can ask the question.
Yeah. Thank you. There is a lot of value to looking at the question first also. So I don't mean to devalue that approach. I think it's largely because we know where they're going in algebra. And so if our mindset is on algebra, which for an algebra class we should do with sixth graders, is different. So, but introducing that then earlier in sixth grade with just understanding the situation, that will prepare them for, in algebra, absolutely reading the language. You want to ask what is the question, because that's where you define a variable. They're not doing that in sixth grade, at least they don't have to. Sometimes though, I would say, some of them just said, I'm gonna call it R, or I'm gonna call it Y. Like they would call some things letters so that they could write those expressions. And I wrote them I chose the most challenging level of problem that was at the end of the year for sixth grade with the carnations and roses. But that's one where some of our sixth graders just started to make algebraic expressions when they had not seen that yet. It could have been, yes, you're right. That would make sense also, right? Because we're so used to an algebraic thinking and not
But then the students actually would go, oh, but it's easier and faster if you just do it this way, would create a paragraph.
right. There could be competing. It's easier to do it this way. And that's not bad either, because if they've learned something from their parents, it's very good to have in the classroom. And there can be confusion with, I want to do it the teacher's way. So, but still the thinking was incredible with those problems by the end of the year. Yes.
Well, what a way to free them up to think through what makes sense for them. I have a son that did that and went into engineering, and he would solve the problems for his tutor and his teacher, and she's like, I don't know, I couldn't follow it, but he got the right answer and he could explain it. So giving them the freedom to do that is really healthy. But a quick example of when you don't teach your children to read math well or to speak it is myself. I studied engineering and I figured out that dividing fractions was about the law of identity and homeschooling my own children.
Mm-hmm.
That's sad.
I've heard that multiple places before from math teachers.
That's sad. Like that should not have happened, right? I was just taught the tricks to do, and I could follow the tricks. So I got the right answers. didn't understand what I was doing.
There are very powerful tricks that can get you through a lot of graduate level mathematics. Yeah. Good. It is time for lunch. Thank you very much for coming, and thank you for the questions at the end.